Okay, calculus, we are looking at optimization. That is just making things big or small. In fact, it's looking for the max or a min of something. Just here's your notes with kind of the general guideline. I'm not going to be writing out this entire process every time, but let's kind of summarize what we do. First, we want to look at assigning variables to things because that helps us measure stuff. If we can make a relationship between different objects or measurements, and then we can make an equation, and then we can start measuring that equation. Sometimes a chart will help us. Generally, what we're going to be looking at with all these things is making the equation, and we're going to call something a primary equation. So we call it a primary equation because it's the equation to optimize. We want to maximize it or minimize it, but we want to optimize some type of equations, and here's a whole set of equations. Now, things that to keep in mind: area of a rectangle or like a box type thing, distance equals rate times time, but we can also move that around to like distance over rate equals time, or distance over time equals rate. If we want to make a maximum rate or a maximum time or a minimum rate or a minimum time, those kind of things help us out. Volume of a rectangular solid, also known as a box, length, width, height, multiplying. Hypotenuse or a diagonal is a thing that we're looking at, is the horizontal plus the vertical squared. Perimeter of a rectangle, pretty standard there. Volume of a cylinder, that's something we're going to be using. These aren't the only ones, but these are things we are going to be using in this packet, but it's not the only ones that ever exist. There's more than just these. The problem with doing these optimization things, which require derivatives in order to max or min things, sometimes you have more than one variable. So we're going to reduce those variables down to just one variable, and we're going to see how that comes into play here in a minute. Take the derivative of the equation, set it equal to 0. We're trying to find maxes and mins. Remember, if we go up then down, that's a max, and if we go down then up, then that's a min. The general things that we've been studying. Then the last thing, or last three things I should be saying here. Be sure that you actually answer the question. Sometimes it's asking when, and sometimes it's asking how much. But we need to make sure that we actually answer the question that they ask us to answer. For these last two, we're going to be looking at endpoints, and we're also going to check it with our calculator using that calc function on the TI calculators that most of us have. So let's get started with the first one. It says two numbers add up to 40. Find the numbers that maximize their product. So this is our equation that we want to maximize, but let's go ahead and start building it here. So the smaller number, let's say 0. The larger number, 40. 0 times 40 is 0. Okay, if I were to go bigger, how about 5? Then this would be 35. And 5 times 35, how much would that be? That'd be 175. If I keep on going with that same pattern, let's say 10 times 30. It looks like we're going to have 300. And 15 times 30, or no, what are we looking at now? 25. So 15 quarters would be 275. Is that right? Yeah, 270. No, 375. Then let's say we did 20 and 20. Well, 20 times 20 is 400. Now something interesting happens. Once this other number becomes too big, the other ones are going to go down. It's almost like if I were to pick 25, then this would be 15 and 375. So it really looks like that this 400 is our maximum here. But how do we prove that with an equation and some calculus and some testing here? Okay, so our product, this is our primary equation. Let's call the first number x and the second number y. That means that the product is equal to x times y. Now I can't take the derivative of this because I have two variables. It doesn't work. We're not looking at implicit differentiation. We want to narrow it down to 1. But secondly, we know that x and y, when we put those together, that's going to equal 40. Now this is helpful because what I can do is I can solve for one of these variables. For example, let's say I solved for x. So I'm going to subtract y to both sides. Then I get x equals 40 minus y. So I'm going to plug in 40 minus y for x. So we have 40 minus y. Now if I were to do some algebra and simplify this, I'd get 40y minus y squared equals p, our product. So that's what I want to maximize. Let's go ahead and take the derivative because that's kind of our next step. Now that we have an equation, not an equation, an equation with one variable, we are ready. So p prime, our derivative, this is at 40, so it's going to be 40 minus 2y. We're going to set that equal to 0. I'm going to move the 2y over, so we have 2y equals 40. If we divide by 2, that gives us y equals 20. Excellent. Hey, that confirms exactly what we said. And if y equals 20, we know that x plus y equals 40, and x plus 20 equals 40. Then we know that x equals 20. So the algebra and the calculus proves it. 20 and 20 are the two numbers. Let's check our question. Find the numbers that maximize the product. Check, we did that. Let's move on. For this next one, we have a rectangle. It's got a perimeter of 71 feet, and it's asking us to find the length and width so that the area is a maximum. And then it asks us a second question here. What is the maximum area? So not only do we have to figure out what is the length and the width, we also have to figure out, well, what's the area? All right, well, let's try this. Let's say we got 1 by 70. Well, now that didn't really work, and here's why. Because when you have a rectangle, if this were 1, then that means this other side is 1. And then if these two sides were split in half, this would be 6, 9. So then we got to split those other two sides in half. That'd be 34.5. 34.5. Because now that would all add up to 71. So if we have 1 and 34.5, then the area is now 34.5. Well, let's say we did like 5. That means we'd have 5 and 5. Well, that makes 10. So then we have 61 left over. So we have 30.5 here and 30.5 here. So 5 and 30.5. And length times width then. So 5 times 30.5, that's going to be 15.25, 152.5. Let's go up a little bit more. How about 10? That means we have 10 and 10. And then for the other sides, we have to split the leftover. That's going to be 51. So 25.5 and 25.5. So 10 and 25.5. That would give me 255. Okay, well, let's see if we can keep going. How about let's do 20? That means I'll have 20 and 20. That's 40. And then on these other sides, that means that we're going to have 31 split in half. So that's 15.5 and 15.5. So we'll have 20 times 15.5. Or that's 30.5, 31 times 10, or 310. Okay, so we got numbers going up. I mean, we might as well, keep on going here. We got 10, 20, 15.5 here. Let's see what happens if we went to, like, let's say 25. If we went to 25, that'd be 25 and 25, that's 50. So that means we have 21 for the other two sides. So that's going to be 10.5 and 10.5, or 250. Well, not 250, 10 and a half times 25. That's going to be 250 plus 12 and a half, so 262.5. This is interesting. Look, we were low, then high, then low. So that means somewhere in here we hit a max. Well, let's see what's going on here. If we have this W, how do we figure out the other one? Well, we got two W's and two L's. And we know that 2W plus 2L equals 71. So to find the L, we have to kind of solve this equation for L. We'd get 2L equals 71 minus 2W. Then we have to divide all that by 2. So this is what we would have. Okay, so that means this is going to be 71 minus 2W all over 2. I know we're getting a little bit small in the writing here, but how can we make that a general pattern? All right, let's kind of go to our primary equation. We need to maximize the area. Well, the area is going to be length times width. But we also know that the perimeter equals 71, which is 2L plus 2W. Well, we can solve just like we did, and we said that L equals 71 minus 2W, all divided by 2. So we can use that. Now we're going to take this piece now and plug it in over here. So that means that area equals W times 71 minus 2W all over 2. So that's what we need to maximize. Let's do some algebra first to kind of move things around here. So if I were to distribute this W, that would help me a little bit. I got 71W minus 2W squared, all divided by 2. Let's take it one step further. That means that the area is really equal to 71 over 2 times W minus W squared. So now this is going to be very easy to take the derivative of. You just do the derivative of area, so A prime. The first term is just 71 over 2. It's a constant because this is W to the first. The second term, that 2 is going to drop down, so we'll have minus 2W. We're going to set that equal to 0, 71 over 2 minus 2W. Keep solving even more. So we have 2W equals 71 over 2. Now we're going to divide both sides by 2 or multiply by 1/2, same thing. So W equals 71 over 4. That's interesting. That means that this side's 71 over 4, and this side's 71 over 4. So I'm basically taking that 71 and splitting it into 4 pieces equally. So what that means to me then is, I have these 4 pieces, they're all the same. That's a square. So this kind of brings up some intuition that we need to be looking at. When we're trying to max a shape, we want symmetry. That implies that we're going to have some type of symmetry. So that means we're looking at squares, circles, cubes, and all those kind of things. We want some type of symmetry taking place. And when it's just a simple shape, you really don't need to do a whole lot of calculus. But what we're going to see is when these shapes have a little bit of imbalance in their measurements, like if one measurement's worth more than another measurement, and so on. All right, let's go ahead and take a look at, oh, no, wait. We know that this is 71 over 4 and 71 over 4, but they were also asking us to find the area, which would be 71 over 4 squared. And I'm just going to leave it at that because you guys can calculate it with a calculator. So let's look at the next one. Find two positive numbers that minimize the sum of twice the first plus the second. And we know that the product of the two numbers is 288. All right, well, let's make this kind of easy. Let's call this x and y. So we have 288 times 1. So we're going to do twice the first number plus the second. So that's 2x plus 1. So 288 times 2, well, that's pretty big there. 288 times 2 is going to be 56 plus another 16. That's big. Now let's just do this out by hand. 16, 2 times 8 is 16, plus 1 is 17, then we got 576. So this is 576 plus another 1. It's 577. Now if we were to drop down significantly, for example, let's say, I don't know, let's divide that by 4. So 288, let's go more than 4. How about, let's divide it by 16. Pretty sure that goes into it. It's going to go in here once, and then 16, when we subtract that, we get 1, 2, 128. And how many times does 16 go into 128? So 10 times would be 160. So we're going to subtract a couple from that. This would be 8 times. So if we have 16 and 18, so then what's 2 times the first number? That would be 32. Plus 18, that's going to be how much? 50. That's a lot smaller. Look at these two compared to each other. Well, we could also do 18 and 16 because those two multiplied to 288. But now we're going to double the first one and only one time the second one. So that's going to be, let's see, 18 times 2 is 36 plus 16. That's going to be 56. Okay, so that's a little bit bigger. So what we're looking for then is trying to minimize this. Let's go the other way. Let's try 288 divided by, I don't know, how about 12? Let's see, 12 goes into this twice, that's 24, and we got 48, so 12 goes into 48 4 times. So let's do 12 times 24, and 24 times 12. Okay, so if I do the second one here, 24 times 2 is 48, plus 12, that's 60. Again, that's probably going to be too big. The second one, though, 12 times 2 is 24, plus 24, that's 48. So here's x, and the second number is 288 divided by that number, and then we add them together. This is like 2x plus y. So now, what is our primary secondary equation? I'm going to erase these things here. Our primary equation is that sum. The sum equals 2 times the first number plus the second number. But we know that x times y equals 288. Again, we're running into this problem because this is, we want to optimize this. We want to optimize this equation here. But the problem is we got two variables. And with two variables, that doesn't really help us. Well, let's get that y out of there. So I'm going to divide by x on both sides. That gives me y equals 288 over x. I'm going to plug that in. So that means my sum equals 2x plus 288. Now I'm going to do something here. I'm going to take this over x and write it as x to the negative 1. And if you're wondering why am I doing that, well, what am I about to do? I'm about to take the derivative. And when you take the derivative, it's nice to have everything in power. So we're going to do s prime equals 2 plus, okay, now we got to drop this negative 1 times 288 times x to the negative 2. Alright, so I'm going to set this equal to 0 and start solving some things here. This is really 2 minus 288 over x squared. If I start doing some algebra, move things around, 288 over x squared equals 2. I'm going to do a combo play here. Divide by 2 on both sides, or multiply by 1/2. And I'm going to multiply by x squared on both sides. That tells me that I'm going to get 288 divided by 2, which is 144. And that equals x squared. Well, then that's a pretty simple square root. It's a perfect square. X equals 12. Hey, that's what we found here with our lowest number. Looks like we were right on. Now the second half of this is figuring out what y equals. Y equals 288 divided by 12, which is, in this case, we already figured that out, 24. So those are two values, x and y, our first number and our second number. It says find two positive numbers. We did, 12 and 24. And you might be thinking, but that's not symmetrical. 12 does not equal 24. But 2 times 12 does equal 24. And we were looking at 2x trying to balance with y. So when these two pieces were symmetrical, when they were balanced, we actually did have the lowest or the optimal value. Let's see what we got next. I think this is the last one for today. It is. This is the last one for this section. I'm going to do the second half of this section afterwards. So we got this open box. Now this is a classic problem that so many people struggle with. It's really not as hard as you would think. So this is what's happening. So I start out with a box on the ground. And then I'm going to make some cuts. So I'm going to cut here and here. And I cut that piece out. And what happens then is I'm going to fold those pieces up. There we go. And then I take this, let's make it like a gray line or something. How about that? So we got orange, we want gray. So on this gray line here, and here, and here, and here, I'm going to fold up these edges. And what I wind up doing then, we're going to take this piece out. We're going to cut that off. We're going to cut this off. We're going to cut this off. We're going to cut this off. And now we have kind of this cross-looking shape. And if we fold on those gray lines, then you get something that looks kind of like... We're going to fold on those gray lines. That's why those gray lines are still there. We're going to get something that looks kind of like this. Actually, I should make those black. Let's make those black. Then we can put these together. Now we got a box. Visualizing this is probably the hardest piece out of all of it. So we got that base, and then we got this box from the sides. And notice the sides are kind of see-through here. But these edges right here, this was X, and this was X, and this was X, and this was X, and then X, and X, and X, and X, are the same as these edges here when they fold up. So this box now has dimensions. We got a width here, a length here, and this X piece equals the height. So when we read this question now that you can visualize it a little bit better, you can see what's going to happen. An open box to be made from this sheet, okay? We're cutting out squares of equal size from the corners and bending up the sides. What size square? So how big X should we cut to create a box with greatest volume? Well, a box is a rectangular prism, and the volume of a rectangular prism is length times width times height. Okay, now that we got that idea going on, our length was 30, But notice that this length and this width have pieces being cut off. We're cutting off x here and an x here. So we got one x and one x gone. So we start with 16. And then we take away a couple of x's. And similarly for the w, that's going to start with 30, but then we're going to take away a couple of x's. So our box, the volume of the box is going to be the length, which in this case we said is 16 minus 2x, times the width, which is 30 minus 2x, times the height, which is x. Okay, now that we're at this point, we can actually multiply this out. So you can do the box method of multiplying, pun intended. We got 16 minus 2x, 30 minus 2x. So let's see what we're going to get. We got 4x squared here. 16 times 30. That's going to be 300 plus 180, so 480. And this is going to be negative 60x. And over here we have negative 32x. So if we were to put all this together, this would become 4x squared minus, let's see, 32 and 60. If we put that together, that's going to be negative 92 minus 92x. We got 480, so plus 480. All times x. Now I could factor out a 4 from this. That might be helpful to me, but I'm going to go ahead and multiply this x through first. So we got 4x cubed minus 92x squared plus 480. So let's go ahead and factor out this 4. That's going to give us 4 times x cubed minus, we got 18x squared here in the middle, plus 120. Is that right? Yep, that's right. Oh, 120x. Can't forget that x. So that's our volume. Let's do our volume derivative. We'll still have this 4 here, but now it's a little bit easier to calculate these. We'll get 3x squared minus 36x plus 120. Now, it might not be obvious about how you would factor this. And I look at it and I feel like we can also pull out a 3. So let's pull out a 3. That means if we pull out a 3, divide each of these by 3. We're going to pull out the 3 here. So we'll have 12 on the outside. We'll have x squared minus 18x. No, what? Minus 12x. Pardon me. Minus 12x plus 40. Right, so now what do we got? What multiplies to 40 adds up to negative 12? It doesn't look like anything does it? No, not really. So that means that we'd have to actually use a calculator at this point. Unless I made a mistake somewhere in the middle, which is totally possible. That happens all the time. Well, let's see. What's 18 times 4? That's 92. That's right. Isn't it? What's 18 times 4? 4 times 8 is 32. Oh, that's only 72. Whoops. So how many times is 4 going to 92? That's going to be twice 23. So this should be a 23, not an 18. So let's see if I can go back and fix some of these errors here. So that's not an 18. That's definitely not 36. And that means that this probably isn't going to factor as simply as it did. So this is actually 23. And 23 doesn't divide by much of anything, but if we pull it down, we got 56 and 120. This is not going to be helpful at all to us. Okay, well then let's see what we could do. We need to do 3 times 120 here. It's actually 46, isn't it? Yeah, 46. 46x. So 3 times 120, if we're to do a diamond factoring, diamond method of factoring, the top and bottom piece, we'd have 360 and 46, negative 46. Now this is not as hard as you would think. It's going to be negative 36 and negative 10. And that actually adds up to negative 46 and multiplies to 360. So that means we have x minus 36 over that a, which is 3, and x minus 10 over 3 equals 0. Now, we do need to multiply a 3 in here somewhere to balance these two x's. So the first thing, we got this 36 over 3 is going to become x minus 12. And then this other piece here is going to be, these 3's will cancel, then we're going to distribute the 3 to the x. We'll have 3x minus 10. So we have two values. We could say x equals 12, or x equals, what's the other one? It's going to be 3x minus 10. That was negative or positive 10 thirds, or 3 and a third. So those are our choices, 12 or 3 and a third. Now I'm going to use some intuition here. I know that the value of this, or the shape of that, is a parabola. And these zeros are happening here at 10 thirds, and then again here at 12. Now if you think about it, we can't even use the 12, because what's our domain here? If x actually goes up to 8 all the way to here, we're cutting all the way off on that side. So x has to be less than or equal to 8, but greater than or equal to 0. So that 12 is even, out of range for us. If that doesn't make sense to you, try cutting 8 inches from both directions without overlapping. Or more than 8 inches, I should say. So right here, this is going to be a maximum value, which also makes sense because the derivative v prime here is positive, then negative. That means it's going up, then down, which means we're going to hit a max. So what's the question asking? So what size squares? So that's not too hard. X equals 12. That's our first question. Our second question is, what is the volume? That means we got to plug in 12. So we're going to have 30 minus 12 times 16 minus 12 times 12. Let's see what these three numbers are. 30 minus 12 is going to give us 18. 16 minus 12 is 4. And then another 12 in here. So that would be our actual volume of the box, our maximum type box. So that's 48 times 18. Let's see what we get. Do this by hand here. 8 times 8 is 64. 8 times 4 is 32, plus 6 is 38. Then we got 48 here, so we're going to have 4 plus 16, carry the 1, so 864. So this equals 864. Pretty sure on that, not positive. Inches cubed. Okay, now here's the biggest thing. This was a lot of work, a lot of work. What I would like you guys to do is watch this multiple times until it actually makes sense. If it's not making sense even after a couple times, it's worth asking questions from friends and from the teacher. So keep that in mind as you go through this. I'm going to stop it here, but I am going to continue the last three problems in the next video.